There's this quiet, invisible energy that powers practically everything we do. It's a hidden force that has, without us really noticing, become the silent heartbeat of our modern lives.
No, seriously, take a look around you right now. Your phone, for sure. Your laptop, probably. What about your watch, your headphones, your remote control, even your car keys? The list just goes on, doesn't it?
Yeah, they really are. These little boxes of power are pretty much the unsung heroes of the 21st century. They are tiny chemical reactors, turning stored energy into the electrical lifeblood for all of our gadgets.
So that's the big question, isn't it? Where did all this amazing portable power come from? And maybe more importantly, what's the real price we're paying for it? Because, as you're about to see, there's a pretty big catch.
Okay, so to really get a handle on where we're going, we've got to look back at where we've been. And our story actually starts with a really old and kind of weird ancient mystery. I mean, just look at this timeline. We're talking about a journey that spans more than 2,000 years. It kicks off with this bizarre 2,000-year-old artifact, the Baghdad battery. Was it really a battery? The jury's still out. But the first true battery, the kind with a steady current, that was Alessandro Volta in 1800. Then, boom, 1859, the first rechargeable battery. A version of that is still in your car. And by the 1950s, we get the modern alkaline battery that pretty much powered the world for decades. At its core, every single battery, from that ancient clay pot to the one in your phone, works on this same beautiful, simple principle. You've got two different materials, a positive side, the cathode, and a negative side, the anode. Separating them is a substance called an electrolyte. A chemical reaction gets tiny particles called ions flowing across that electrolyte, and that pushes electrons out into a circuit. That flow of electrons is electricity. It's so simple, yet it's absolutely revolutionary. So that basic science set the stage for everything that followed. But then, in the early 90s, one specific type of battery chemistry came along and just changed the game completely. I'm talking, of course, about lithium-ion. And the real secret sauce to this revolution wasn't just the tech. It was the price. Just look at this. A little over a decade ago, you were looking at about $1,000 per kilowatt hour for this kind of power. Today, it has absolutely plummeted to under $200. That is a massive, massive drop, and it is the single biggest reason our world is filled with battery-powered tech. All of a sudden, you could have these powerful, long-lasting, lightweight batteries that were actually affordable enough to put in, well, everything. This wasn't just a small improvement. This was the key that unlocked the smartphone in your pocket and made the electric vehicle a reality for millions of people. But, and this is a really big but, this is where our story takes a sharp turn. Because all of this incredible progress, this amazing clean energy future we're all building, it rests on a foundation that has some very, very dark corners. This quote from earth.org just nails it. This mineral conundrum, it's the perfect way to describe the problem. To build our green future, we need very specific minerals, and the way we get those minerals is often anything but clean. To really see what that means, let's start with lithium. A huge amount of the world's lithium comes from the so-called lithium triangle in South America. The process is pretty wild. They pump enormous quantities of salty water from deep underground into these huge, sprawling ponds, and then they just wait for up to 18 months while the sun literally bakes the water away, leaving the concentrated lithium behind. And just try to wrap your head around this number. It takes over 2 million liters of water. That's like enough to fill an Olympic swimming pool to produce a single ton of lithium. And this is often happening in some of the driest places on Earth. It's a staggering environmental cost. But honestly, it gets even worse when we talk about another key ingredient, cobalt. So over 70% of all the world's cobalt comes from one place, the Democratic Republic of Congo. And the insane demand for it has created this boom in what are called artisanal mines. These are often just unregulated holes in the ground where workers, sometimes children, are digging by hand in unbelievably dangerous conditions. The human toll is immense, and the toxic runoff from it all poisons the water, the crops, and entire ecosystems. And we see images like this all the time, right? The sleek, clean, efficient promise of a future powered by batteries. But we now know that this clean image is, well, it's only part of the story. The reality of where these raw materials actually come from is so much more complicated and often so much more damaging. And what's so jarring is the contrast. I mean, on one hand, you have this incredibly precise, meticulous science. Look at this, engineers measuring a battery's performance down to the millivolt. And on the other hand, the very beginning of that supply chain can be so crude, so dangerous, and so destructive. That's the paradox.
So, here's the billion-dollar question. Can we fix this? Can our own ingenuity get us out of the very problem it helped create? You can think about it like this. The first wave of innovation solved problems like cost and performance, range anxiety in electric cars. We pretty much cracked that. The next wave of innovation has to solve the environmental and ethical costs. That's the new frontier.
And the good news is, there are some really promising new ideas on the horizon. Sodium-ion batteries use superabundant and cheap materials. We're talking salt. Solid-state batteries could be a huge leap in safety and power. And then there's lithium iron phosphate, or LFP, which is already a huge deal because it's completely cobalt-free.
You see, the path forward isn't just one magic bullet solution. It's a whole bunch of things at once. It's designing batteries that don't need cobalt, like the LFP batteries Tesla's already using in half its new cars. It's investing in these brand new chemistries. A huge piece of the puzzle is recycling, getting really good at recovering over 95% of those valuable materials from old batteries. And hey, maybe it's also about thinking bigger and designing cities where we depend a little less on individual cars in the first place.
Which brings us right back to where we started. Our relentless demand for portable power has created this difficult paradox. We're caught between the clean future we want and a pretty dirty present. The challenge is immense. There's no sugarcoating that. But the innovation is happening faster than ever. So the real question isn't if we can do better. It's how quickly our ingenuity can rise to meet the challenge.